This is Physics 241 Laboratory. We're talking today about lab number 5, and our topic will be friction. As a little bit of background, as you all know, Newton has 3 laws of motion. The first law is that a body in motion stays in motion until it's acted on by another force. A body at rest stays at rest until it's acted on by another force. In earlier labs, we met one of those forces, gravity. This pen will stay at rest until it's acted on by gravity, in which case it'll fall. We covered that in labs 2, 3, and 4. But another force, outside force that acts on objects, is friction. And we'll talk about that today. Newton's second law is force equals mass times acceleration. We will also talk about that in today's lab. Part B of this lab will cover F equals ma. And Newton's third law is for every force there's an equal and opposite force. F equals minus F. And we will cover that topic in later labs. Today's lab covering friction. And we're going to deal with both static and kinetic friction. Static friction is kind of what the word indicates. It's still. Kinetic friction means moving. If we look at that as a block, static friction is the amount of friction that's needed to start this block moving at the very instant it moves when it gets pushed. Kinetic friction is the amount of friction that's generated once the block is moving. So static is to get it started, and kinetic is to keep it moving. And as you would suspect, static friction is normally greater than kinetic friction. It takes a larger force to move an object completely still than it does to move an object that's already in motion. If we look at a typical block, we know if we're going to push the block this way, that there's going to be a friction force that's going to be acting on it this way. When we talk about a normal force is simply the weight of the object times gravity. Our formula that deals with this is the friction force equals what we call the coefficient of friction, mu, times the normal force. Now, our coefficient of friction is normally less than 1. And that's because if a friction force was greater than 1, it would be greater than the force itself. So what the coefficient of friction is showing is what percentage of the force is needed in order to overcome the friction force. We would designate mu sub s as the coefficient of friction for static friction, mu sub k as the coefficient of friction for kinetic friction. And today's lab has 2 parts. In the first part, we're dealing with a block and a weight. And we're going to use a force sensor to pull on that block and weight. And we're going to generate graphs, and through those graphs we're going to measure the force that's required to pull those blocks and weights, and we'll be able to, from that, calculate our mu, both static mu and kinetic mu. Second part of the lab, we're going to do the same thing. We're going to use a sliding block or a weight, but we're going to use a motion detector. And using the motion detector, we're going to generate a v over t graph, and with that we can determine acceleration. Knowing the acceleration, knowing F equals ma, we know the mass, we know the acceleration, we'll be able to calculate the F, and then knowing this equation, we'll be able to determine the mu sub k. Now in our first instance, we're talking about using a force sensor. We have a block here.
Wait a minute, please.
And we're going to pull on the block with the force sensor measuring the force. Now, normal force would be the mass of the object times 9.8 meters per second squared, which is gravity. What we do when we pull on this block with the force sensor, we're going to generate a force over time graph, which we show here. And that's kind of what it should look like. And at the top of this graph is going to be the amount of peak force in a static situation when that block first starts to move. And then the blocked area here will be the average force once the block is moving. Now, we can use our statistics tool in our computer programming on the Vernier program to determine these forces, both the peak static force and the average kinetic force. If we look down here at this chart, we do 3 runs or 3 scenarios. The cart itself weighs about 0.3 kilograms. We do a second run with the cart plus a 5 kilogram weight added to it. And then our third run will be 1.3 kilograms, which is the cart plus a 1 kilogram weight added to it. How we calculate the normal force is the mass times 9.8. So our normal force will be 3, 7.8, and 12.7. From our program, we were able to determine the static force in newtons, 1.09, 2.55, and 4.07. And the mu would simply be the F divided by the N. And we're coming up with something like around 0.3 for our mu static. The average of mu static would be 0.336. Now, to do the kinetic coefficient of friction, again, we're using the forces from this program, the average kinetic force, which we measured for these 3 scenarios. And these are the kinetic forces, 1.07, 2.07, 3.01. Again, knowing the force, knowing the normal force, we can calculate the mu sub k. And we're coming up with a mu sub k here of 0.286. So static, it's 336. Kinetic, it's 286. Obviously, 0.286, 0.336. And as we suspect, the kinetic friction will be less than the static friction, and of course they both will be less than 1. We kind of do a repeat in part 2 in that we're going to check for the coefficient of kinetic friction only in this scenario. In this scenario, we're going to have a block and we're going to push it. We're going to have a motion detector and it's going to record the motion of the block. We're going to do 2 different scenarios, the block itself at about 300 grams and the block plus a 500 gram weight added to it. We're going to do 3 trials for each of these 2 scenarios. We're going to generate V over T graphs. Again, using our computer program, it should look something like this. And what we're going to do is we're going to zero in with linear fit, their linear fit function, to determine the slope of this line at the decreasing speed of the block, when the block starts to slow up after we push it. That's the acceleration due to gravity, A. From this graph, we can determine A. And in the first case, we came up with 2.37.
Wait, you had to stop. I had to back up here.
And in our second case, again 2.37, for block and block only. We know F equals ma. Knowing A, F equals ma, we know the mass of the block, we know the acceleration of the block, we can calculate the F. Again, mu sub k is F over the normal force. We know we can calculate the normal force. Weight times gravity, which we have right here. The mu sub k would be the force, 0.72, divided by the weight, which is 0.3 kilograms, and gravity, 9.8. We're getting a mu sub k of 0.24. We do the same thing in the second scenario. We also get a mu of 0.24. And we found out that in both cases, regardless of the weight, the mu sub k was about 0.24. And in our first part, the mu was about 0.286. So they are fairly close. Again, validating the data here. And in both cases, of course, both with U sub k and U sub s, it's less than 1. That concludes the friction lab.